Hello and welcome to Sean White's Solar and Energy Storage Podcast. The title of this podcast is Energy Storage System Code in the NEC, besides Article 706, Energy Storage Systems. And by the way, Energy Storage Systems is always abbreviated ESS, and the NEC stands for the National Electrical Code, which is published by the National Fire Protection Association. That's the NFPA. So now what we're going to do is we're going to go over the NEC, talking about things that have to do with energy storage that are not in Article 706, Energy Storage Systems. We're going to start off talking about Article 90, that's the introduction. Article 100, definitions. Article 110, requirements for electrical installations. Article 200, use and identification of grounded conductors. Article 240, overcurrent protection. Article 250, grounding and bonding. We're going to also mention the Soares book of grounding and bonding. Then we're going to talk about Article 310, conductors for general wiring. Article 358, you know what that is? That's EMT, or electrical metallic tubing. Then there's Article 480, storage batteries. And then we're going to talk about Chapter 5, which is special occupancies. And that includes aircraft hangars, but you probably already knew that because you were learning about that when you were designing a hangar electrical system for your private jet, just like I was. So remember, to learn more about energy storage, go to solarsean.com. On with the show. Here we are back at the National Electrical Code, now the different parts of the NEC that have to do with energy storage systems, but are not titled energy storage systems. So we have to follow the other parts of the National Electrical Code, and typically we're talking about chapters 1 through 4. But before chapter 1, we have very short Article 90. And Article 90 is just a little introduction article to the code. It says what the code covers. So, for instance, it doesn't cover electrical installations in ships and cars, things like that. It talks about the arrangement of the code. So chapters 1 through 4 applies to all electrical installations. But other chapters modify chapters 1 through 4. So if we're going to go look at chapters 5, 6, and 7, they modify chapters 1 through 4. Chapter 8 is kind of on its own. It's a communication system chapter. Then we use tables in chapter 9. And then there's some informational material that we have in annexes at the back of the code. Now, one of the things that we talk about a lot is the AHJ, the authority having jurisdiction. If you want to know about the authority having jurisdiction, it's usually just the building department, but it could be an insurance company or a utility or anybody that has powers to oversee what you are doing. So, for instance, if you're doing work on a military base, your AHJ could be the federal government since it's federal property. So if you ever are doing a federal job, just be aware that you might be on a different version of the National Electrical Code. And they typically adopt the code right away, right when it comes out, just like Massachusetts, which means the 2023 National Electrical Code would be adopted on January 1st, 2023. And that takes us to the end of this little introduction, which is Article 90. Then chapter 1, we have Article 100, definitions, which there'll be some energy storage system relevant definitions, definitely. And then we have Article 110, requirements for electrical installations. So one thing that's kind of important in Article 110 is space about electrical equipment. At 110.26, that talks about your working space. 110.26, spaces about electrical equipment, and it just tells us how much space we need around our electrical equipment. Another thing that could be relevant too would be Table 110.28, and that's enclosure selection. So you might have heard of NEMA enclosures. NEMA means National Equipment Manufacturers Association. Now we're going to take a peek at Chapter 2, and that stands for wiring and protection. And so some of the things that are going to be in Chapter 2, wiring and protection, are Article 200, which is use and identification of grounded conductors. So a grounded conductor is also known as a neutral. A grounded conductor is typically going to be a white wire in the United States, which would be a blue wire in most of the rest of the world. Once in a while, it's a black wire in some countries. And these grounded conductors are going to be wires that carry current but have the same voltage as ground. So a grounding conductor, that ends with a G, would be like an equipment grounding conductor or a grounding electrode conductor, and those would be green wires or bare wires, but a grounded conductor ends with a D, not with a G, is going to be that white wire, that neutral. If you looked at your plug socket on your wall, it's that upper left prong, the one that's a little bit bigger than the one on the upper right prong. That is a grounded conductor. So if you took your wall apart, you would see that there's a white wire going to that. Go ahead, take your wall apart right now. I'll wait. So anyway, we've got Article 200, grounded conductors. 210 is branch circuits. That goes to your loads. 215 are feeders. Okay, 220, that's for branch circuits. That's more like for loads. 225, branch circuit feeders. 230 is services. So a lot of times when we go to Article 705, it's going to refer us to Article 230 services. And so a service is where the utility serves you your electricity. That's called a service. Okay, Article 240, and that's overcurrent protection. Overcurrent protection is a fuse or a circuit breaker. It's very important. It protects wires. If too much current comes in, we're going to be protected with overcurrent protection. A lot of times you will see OCPD as the abbreviation for overcurrent protection device. So just if you're OCD, then you can just go over it over and over again and go, hey, that's OCPD, not the Orange County Police Department, because that would be a sheriff anyway, but it's OCPD, overcurrent protection device. Not to be confused also with obsessive compulsive disorder. And then we have overvoltage protection. We don't tend to be using that too often. Grounding and bonding, a very long article in the National Electrical Code is Article 250, grounding and bonding. The way that I look at grounding and bonding is it is not a perfect science. So that means that you're going to get lots of different experts from lots of different places having lots of different opinions on how to do things right. And it really depends on where you live, how they're going to make you do things. They're going to make you do grounding and bonding different on a supply side connection in Chicago versus grounding and bonding in other parts of the country, such as grounding and bonding of a supply side connection in California, for instance. It's going to be completely different in different regions. So you kind of have to know what they're looking for. Sometimes they're more concerned about lightning, say if you're going to be in a place like Florida. Sometimes they're worried about ice and wind shaking your wires, and you might need a bigger wire. There's lots of different ways to look at this. Some people spend their whole lives being experts on grounding and bonding. When an electrical inspector comes and inspects a PV system, they are used to inspecting grounding and bonding on other systems, and so a lot of times it seems like they're picking on you for your renewable energy system grounding and bonding because that's what they know. Grounding and bonding has the same rules for alternating current and direct current for the most part. So like I said, this is a super long article. Another thing about grounding and bonding is, just to be technical, grounding is connecting to ground, connecting to earth. In fact, in many countries, they call it earthing. So if you're in a different country, you might want to call it earthing instead of grounding. And then bonding means connecting everything together. So if you're connecting different pieces of equipment together, that means in case there's a loose wire, if that wire comes loose and touches a piece of equipment, and somebody touches that piece of equipment with their hands, they won't get shocked if everything's at the same voltage. So if everything is bonded together. So we bond together different pieces of equipment. But in the field and other places, when they mean bonding, they say grounding. So a lot of times when people mean bonding, they say grounding. In fact, the wire that does the bonding is called the equipment grounding conductor. Why isn't it called the equipment bonding conductor? But it's called the equipment grounding conductor, the EGC. The EGC, the equipment grounding conductor, that does bonding. And grounding could be done by the equipment grounding conductor. And so remember we talked about those Article 200 wires being white. Well, these grounding and bonding conductors are typically green or bare. One of the reasons why they can be bare is because you want them to bond to things. You want them to touch more things. The more things they touch, the better job they're doing. And there's just a lot to this. You could probably spend your whole life studying Article 250 and still not totally understand it. So if you want to get really deep into grounding and bonding and become the smartest person in the world about grounding and bonding, one place you can look, it's called Soares, grounding and bonding. And so Soares makes a popular book that explains how and why certain grounding methods are used. There's lots of different reasons why grounding is done in different ways. Sometimes the earth is more conductive in certain places than others. Sometimes you worry about lightning bolts. Sometimes you worry about electrical wires falling down from high voltage equipment. Sometimes you ground fences and large utility scale photovoltaic systems. So, hey, get grounded. Now, after Chapter 2, because Article 250 ends Chapter 2, Chapter 3, and that's wiring methods and materials. So it starts off with general requirements. Those are usually things that they don't know where else to put them in the NEC. And so then we're going to go to Article 310. And if you're a wire sizer, which is very complicated, you will spend a lot of time in Article 310. In fact, if you wanted to learn wire sizing in depth, in my book PV and the NEC, which covers energy storage, we have a chapter on wire sizing. I also have a chapter on wire sizing. My other book, PV Engineering and Installation. And one thing about wire sizing is that it is super complicated. Most people out there doing it are doing it wrong, but they're doing it wrong and they always err on a side of having a wire that's bigger than they need. So that's why it's not dangerous. And then there's going to be overcurrent protection requirements and requirements for conduit and also the ampacity. So ampacity, what that means is the wire's ability to carry current. And the ampacity table starts off with 310.16 and 310.17. Another thing now is if you have more than 3 current carrying conductors in a raceway or a cable, then you're going to have to derate a little bit more. Let's say that I had 4 wires going together in conduit. So conduit, that's a word for a pipe where you put wires. And so then that's an 80% derating. So remember, we had 40 amps times 0.91. That was for that ambient temperature derating, and that gave us 36.4 amps. Then we're going to have 4 current carrying conductors in conduit. So then I'm going to multiply times, that's 80%. That means 0.8, and that gives me 29 amps. So now my number for the ampacity is only going to be 29 amps. That's a little bit of wire sizing. That's a few of the different checks with wire sizing. You do this check, you do that check, you do all these different checks, and then you come up with a proper sized wire. Sometimes people hire me to do consulting and I do wire sizing. And you know what? Every time I've been hired to do wire sizing, I've never found anybody that did it right. There's people designing systems for big solar projects and they're getting their wire sizing wrong. They're using a wire that's bigger than they need to have there, so they're doing it safer. However, sometimes you don't get the job if you use a wire that's too big because you won't make a profit, and it's not good to not make a profit. So I can check up on these people and do the wire sizing properly. One of the things I do. And so I just want you to know that you're not expected to be the top wire sizing expert in the world. In fact, the top 2 wire sizing experts in the world might even disagree on how to do wire sizing correctly. The NEC sometimes contradicts itself, so you can get different people looking at things different ways. Say, for instance, you look at the Old Testament. You've got the 3 major religions of the world that use that, and they definitely disagree on how to interpret it. And the same goes with the NEC. They'll have lots of different disagreements on how to interpret things. Okay, now we're going to start going through medium voltage. That is going to be a higher voltage than we're going to be dealing with a lot of times. If you're going to be doing medium voltage cable, we're talking 2,000 to 3,500 volts according to this article of the NEC. There's lots of different definitions for medium voltage, but medium voltage means it's a lot higher than most anybody's going to be working with unless you are specialized to work with medium voltage. So typically, if you're working with an energy storage system, you're not going to be seeing medium voltage unless you're working with a utility scale system and you are connecting to medium voltage transformers. And that can go up to 35,000 volts. A lot of you probably think that's high voltage. In fact, it's kind of interesting when you go to an electrical installation, it's not too uncommon to see people put high voltage next to 480 volts. Just remember, there's different definitions for medium voltage. Then we have different rules for different enclosures and outlet boxes and 312 and 314. And now when we get to 320, all different types of wiring methods, armored cable. And so 330 is MC cable. That's something that you might end up using. Then there's 334. That's NMC, or non-metallic cable, NM or NMC. And that's also known in the industry as Romex. Romex is a brand name. So that's probably going through your walls where you're sitting right now, probably powering your computer if you're at home. Then we have some other cables that are not as common. And then we have service entrance, or USE or USE2 cable. You might be using that. IMC, that's a good heavy duty conduit. That's intermediate metal conduit. And then RMC, rigid metal conduit. IMC and RMC pretty much follow the same rules. Flexible metal conduit. This is another popular one that people oftentimes use. Liquid tight flexible metal conduit, LFMC. And then rigid PVC, also known as PVC, or people just say plastic. And then we're going to go through some things that are not as common. And then LFNC, liquid tight flexible non-metallic conduit. A lot of people just call this liquid tight. Then we have a very popular type of conduit that you see all over the place. If you're in your garage, you might see it right now, or in a warehouse, and that is EMT, electrical metallic tubing. Maybe you already know what this is. Flexible metallic tubing, electric non-metallic tubing. Gutters. So gutter is sort of like a big box where you just have a lot of wires that make connections. Those are gutters. Busways, so it's a place where you have big bus bars, a busway. You have pieces of metal that are connected to wires. That's a busway. Cable bus. And we're going to just kind of skip through some things that are not as popular, not as relevant. There's a lot of things in the National Electrical Code that nobody uses, such as knob and tube wiring. People haven't used that for a long time, but if you were working on a 100-year-old house, good chance you might see some knob and tube up there. And those are a lot of times you go up in the attic and you just see bare wires. So knob and tube, kind of famous for being kind of dangerous. Okay, now on to Chapter 4, which is equipment for general use. And then what that's going to bring us to is something that is kind of relevant to what we're talking about, and that is going to be storage batteries. And there's other things that just are these different pieces of equipment that don't have as much to do with energy storage systems. So we are getting into storage batteries. And one thing that I just want to mention is that Article 480 competes with Article 706 energy storage systems. And probably you're going to be following Article 706. They almost got rid of Article 480, and there's people that still want to do it. But they say it's the telecom people that are keeping this here, so they don't have to follow as strict of rules. You're typically talking about lead acid batteries, or maybe some nickel-based batteries. We got NiCads in there. So some of these Article 480 definitions that only apply when you're doing 480. Cell, container, electrolyte. Electrolyte is the ion transport mechanism medium. Nominal battery voltage. In fact, I actually made a proposal, which I believe is going to get adopted into the 2023 National Electrical Code, to get rid of this because there's different voltages of lithium-ion batteries as we've gone over. This wouldn't cover lithium iron phosphate. I didn't really say to get rid of it. I said we should add lithium iron phosphate, and then other people were like, well, let's just get rid of it. It's only an informational note anyway. And now with the new technology too, we're going to just see different nominal voltages. Remember, a nominal voltage is a cell voltage. So every time you have a battery cell, no matter how big it is, it has a voltage based on the chemistry of that battery. So most of the batteries that we're talking about in this class, we're going to say have a nominal voltage of 3.6 volts, because that's your majority of your lithium batteries, has a nominal voltage of 3.6 volts. However, we might discharge them down to 2.5 volts, and we might charge them up to 4.2 volts. This is the nominal voltage, so that's the voltage name for a convenient designation. So let's just read this because this is important. Nominal voltage for a battery cell. The value assigned to a cell battery of a given voltage class for the purpose of convenient designation. The operating voltage of the cell battery may vary above or below this value. So they are saying it's for convenient designation. I always say that nominal starts with an M, is in name only. So we have some batteries that are sealed that you can't add electrolyte to, like all our lithium batteries. You don't go adding electrolyte to a lithium battery. So let's just read the storage battery. A single or group of rechargeable cells connected together electrically in series, in parallel, or combination of both, and comprised of lead acid, nickel cadmium, or other rechargeable electrochemical types. Storage battery. Terminal is what you connect to. That's the terminals, is the terminal post of a battery. But just throughout the electrical code, you're going to see when it talks about terminals, that's where you make the connections. You make a connection to a terminal throughout the code. One of the things that we like to do is to criticize Article 480 because we're Article 706 people. Storage batteries and battery management equipment shall be listed. So that's a good idea. Listing things. And there's UL 1973. That's the UL listing that's a lot of times used for our energy storage systems. But then this requirement shall not apply to lead acid batteries. So you could almost say here that you could go make some lead acid batteries in your basement. Doesn't that sound exciting? I love working with lead. No, not really. So just remember this too, that any type of battery pretty much that carries a significant amount of energy could be shorted out and could cause an explosion. So if you made your homemade batteries in your basement, they might be dangerous. I've never heard of anybody doing that in this century, but people have done it before, and you never know what you might find on YouTube. So with lead acid batteries, a lot of times people have corrosion. There's going to be connections between the cells inside the batteries. A little about like the terminals. You don't want to strain them too much. There's going to be requirements for how you space things around batteries. Another thing that's interesting that I actually put in a proposal to change this is that disconnecting means shall be provided for all ungrounded conductors derived from a stationary battery system with a voltage over 60 volts. So this means that if you were using Article 480 and not Article 706, that if you went under 60 volts, which is pretty common, so you've got 48 volt battery systems that are really common, and that means that you don't need a disconnect. Is that safe to not have a disconnect? This is something that they do on cell towers because they're just saving money. They go there, they hook it up, they just figure they're never going to turn it off. People need to be on the phone, and they're qualified people, and they're probably being safe. But for somebody in their house, we don't want to have this happen. So I was proposing that you say that if it's in a place like a house or building, that you would want to have a disconnect under 60 volts. That's right, I'm on these different committees to propose things like that. Okay, now 480.7, emergency disconnect. 1 and 2 family dwellings, we always see that in the National Electrical Code. For 1 and 2 family dwellings, it says that a lot. We need to have a disconnect or remote disconnect that's going to be readily accessible, so easy to get to outside of the building, and it says emergency disconnect. So if there's a fire and the building's burning down, somebody should be able to push a button to turn off the battery system. However, when we were going through Article 706, energy storage systems, there's something similar to this, and I did point out that in some cases this could make something more dangerous because somebody might be putting some big wires going from inside their house to outside their house, back inside their house. So it's going from the battery to the disconnect to the inverter, and they're running these extra wires that are energized, and that could make it a little bit more dangerous and more expensive rather than just having the system shut off at the battery. But hey, there's different ways of looking at that. And so if somebody had the remote switch, that would be safer than running big cables from your battery to the outside of your house, to the inside of your house, back to the inverter that's sitting next to the battery, for instance. And so if you're connecting a whole bunch of batteries in series here, and you need to be able to have disconnect for sections that are 240 volts or less. Remember, this is not for energy storage systems. So if you have a listed energy storage system that has a voltage that's higher than 240 volts, that's not a problem because you're using Article 706, not Article 480. And then let's get moving, talk a little bit about remote actuation, busways. That's like a bus bar, busway. Let's look at the exception first. If it's a 1 and 2 family dwelling, you just need to have the nominal battery voltage. Available fault current with a battery will change over time. As it gets older, the fault current would decrease. And so that would be a fault current like if you totally shorted out a battery, not something that you're ever going to test for, but you would have to work with the battery manufacturer to figure out what the available fault current is. It says from the battery equipment supplier. And something about an arc flash label. An arc flash is an accidental explosion pretty much. And then also if you're putting these arc flash labels and the available fault current, you want to put the date where you performed that calculation. You want to have a plaque or directory that shows you where these different power sources are. That's common throughout the code. And then battery locations. So we need to have ventilation appropriate for battery technology. It used to be that it just said that we had to have ventilation and people were required to ventilate even lithium batteries that don't put off gases. But if you have lead acid batteries, that's when you need ventilation. And lead acid batteries, As lithium gets cheaper, lead acid is going more and more out of style. Some people thought we would never get here, folks, but lithium is getting cheap. We need to guard live parts, so just think if you had a bunch of batteries in your garage, you don't want your kids setting their metal bike frame on the batteries where there's terminals, so they need to be guarded. There's also special spaces that have to be around batteries. NABCEP, that's a North American Board of Certified Energy Practitioners, actually had a test question which required people to go to 480.10c. So we're talking about batteries with the terminals on the tops. Sometimes they're on the sides. But on your car, it's usually on the top. Actually, my car, it's on the side. Tells you how to get in and out of the room. That's the battery room. Gas piping shall not be in your battery room. Also, it's a good idea to have illumination. So that means lights. And that means lights shall be not controlled by automatic means only. So if your lights come on automatically when you're there, you have to keep waving your hand to keep them on, maybe you need to just have a switch also, or not just maybe. So then you just have to have a switch also that will make sure that it stays on. Don't people have something better to do than to come up with rules like this? Okay, vents. We were talking about vented cells. So this is typically a lead acid thing when you can make hydrogen gas by overcharging the lead acid batteries. So vented cells need a flame arrestor. Sealed cells have to have a pressure release vent, so a sealed maintenance-free lead acid battery. If it gets overcharged, it's possible that it could get overcharged fast, and then the hydrogen and oxygen don't recombine under pressure, and then you don't want your battery to explode, so it's got to have a pressure release vent. So now we're talking about battery interconnections. So flexible cables, as identified in Article 400, which is flexible cords and cables. A lot of times what happens is you end up having lower voltage, so you have higher current with these lead acid battery systems. And so that means you need to have bigger wires for the higher current. It's due to the lower voltage. And these bigger wires, they're really hard to bend. And people are doing maintenance on batteries, so they like to use flexible cords and cables. There's special rules for these flexible cords and cables, and you have to connect them together properly. And one of the things that has happened in the past is people will be using these flexible fine-stranded cables with screw-in terminals. And these screw-in terminals that they're using are not rated for that flexible fine-stranded cable. And so then when you screw down that terminal, the wire gets loose, it creates resistance, creates heat, and it can melt the plastic around the battery. So you don't want to have that happen. So make sure you use the right type of terminals, or better yet, move over to Article 706, where we have batteries that have higher voltages, and we don't need these big cables that you need for the lower voltages. Now, last but not least, lucky 480.13 ground fault protection. If you're over 100 volts, you need to have some kind of ground fault protection. And then at the end of Chapter 4, we have equipment over 1,000 volts nominal. So there's special requirements that people like to avoid as much as possible for systems that are over 1,000 volts. In fact, if you're working with a PV system, you're exempt from using 480 when you're going under 1,500 volts. So people try to keep their systems under 1,000 volts when they're working with batteries or energy storage systems, so they don't have to have these special super expensive pieces of equipment like overcurrent protection devices. And that is for Article 490. And then with 311, it says medium voltage, 2,000 volts to 35,000 volts. So that is just too weird, right? So it's like if over 1,000 volts is high voltage, so 1,000 to 2,000, oh, that's high voltage. Then you get up to 2,000, oh, now we're down to medium voltage. They just contradict with each other. There's lots of different definitions. It makes things a lot more difficult when you have to apply Article 490. And so that's something that most electricians don't want to have to do. Okay, now we have finished Chapter 4. Many people also think that storage batteries should not be in Chapter 4, equipment for general use. It should probably be in Chapter 6, special equipment. That's where we see photovoltaic systems. But it was brought there back in the days of Thomas Edison, where everything was DC, some will say. So it's just a relic that we can't seem to get rid of. That's Article 480, storage batteries. And it leads to a lot of arguments over people trying to apply 706 and 480 at the same time, and they contradict each other. And that's just the code. The code contradicts itself. It's not perfect like we are. Okay, now what we're going to do is we're going to talk a little bit about Chapter 5 special occupancies. And so this is not applied to everything. It's only for special occupancies. So special places where you're going to use special wiring methods. So if you have an aircraft hangar, it's kind of fun. I wish I had an aircraft hangar. Actually, I did before. And it's a great place to store your old clothes. And then you have gas stations, otherwise known as motor fuel dispensing facilities. How many times have you been driving down the road going like, hey, honey, let's go to that motor fuel dispensing facility, gas station. And then this thing, bulk storage plants, we're not talking energy storage. We might be talking where you're storing something different, maybe like fuel or gas, something else that's just not energy storage. So we're not going to worry about that bulk storage there. Special industrial processes, hospitals. If you're doing work on a hospital, there's special requirements that you have there. Theaters, amusement parks, carnivals, movie studios, manufactured buildings. I know I was going to do some solar on a mobile home in California, and it was required to go to the state for your permits because it's a mobile home. Agricultural buildings, mobile homes, manufactured homes, RVs and RV parks, trailer parks, marinas, special requirements for marinas, all that water around there. And if you really want to get confused about grounding, study about grounding for boats, temperature installation, and temporary installations. So that brings us up to the end of Chapter 5. So try to remember everything we just talked about in this podcast or play it again. And to learn even more, go to Solar, S-E-A-N, that's SolarSean.com.